Welcome back. In this video I'm going to introduce multiple linear regression, which is the most versatile approach to statistical modeling that we're going to be looking at in this course. So what's statistical modeling? Just briefly. The idea is, like in any kind of model, that we're trying to find a simplified description of the relationship between various parts of our data, and that we can then use that to make predictions about future data or about just other situations. Any model will only explain part of the data, so it's often said that all models are wrong, but some models are clearly useful. A very intuitive model that we often use in everyday life would just be to expect that something will be average. So if I just buy some apples on the market, my expectation would probably be that the price that I pay is just the average price for apples. In many cases, we might want to be more precise so that we are surprised less frequently. So we might want to add some additional factors, some additional variables. Multiple linear regression is a really good method to add many different variables to a model and see how they together shape a certain outcome. So in this video, I'm going to first recap briefly what simple linear regression was all about, because that's the foundation. And then from there, we can extend the simple model by just adding additional variables. We can add different combinations of categorical and continuous variables. I'm going to specifically exploit up to this point of having two continuous and one categorical variable, because up to that point we're actually able to think about it mathematically, programmatically, so how do we do it in R, and geometrically. And it's really helpful to try to keep those three ways of thinking about it together, because for most of us, thinking about it geometrically makes it easiest to get the intuition right. We can add more variables, the geometry just reaches its limit. Linear models are the foundations for all kinds of statistical tests, so in the end I'm going to give one example for where that is the case. But starting from the very simple linear regression is the example I discussed in the video a couple of weeks back, where we can see that the median age of a constituency predicts or can predict the conservative vote share in that constituency. In the last video it was actually 2017 data, now it's 2019 data, and the relationship is almost identical, so there seems to be something going on here. Once we see such points, we can try to fit a line through them, and that line of best fit that's as close as possible to the points is then the regression line. It doesn't explain the data perfectly, since for that all the points would need to be on the line. Instead, each point has a residual associated with it, so a distance from the line. Still, in spite of all these deviations, we can say that on average, for each year in additional life expectancy, the expected conservative vote share goes up by 1.7%. And taking the result of that as our estimation will be better than just expecting all constituencies to vote the same. Mathematically, we need to estimate two numbers. We need to estimate the slope of the line, and we need to estimate the intercept where it crosses the y-axis. That together then gives us the regression equation, but the interesting part of the equation really is this one slope, Because this one slope tells us that if we move one step along the x-axis, we need to move a certain number along the y-axis for our next predicted value. And that then evidently is a good measure of the impact that one variable has on the other. We can best get these numbers from the LM function in R. We just need to specify what test we want to carry out. In this case, we want to see how the conservative share is predicted by the median age. And we can get quite a lot of output, but just two things are really worth looking at right now. One is the coefficient, so how steep is the line, and the other is the R squared, because that gives us insight into the balance between how much the model explains and how much error we still have. So here the model explains 30% of the variation in conservative vote shares, so there's still a lot of unexplained variance, error, but certainly 30% is a lot more than nothing, so it's a workable model. Still, we might try to make it better by adding additional variables, thinking about additional factors. One thing that might come to mind is whether there is an urban-rural distinction. We can test it quite nicely because in the UK there are two separate types of constituencies, county constituencies and borough constituencies. And actually, if we look at them, there's a big difference in the median conservative vote shares between the two types of constituencies. So if you forget about the analysis we've done before, and now just, for example, do a t-test on this, we can certainly conclude that the constituency type has a really big impact. However, there's a complication, because the constituency type is also quite closely linked to age. Rural constituencies, county constituencies are much older than borough constituencies. How can we put the two variables into one model to see their contributions or lack thereof at the same time? So if we plot it, we might get the idea of now fitting separate lines. And the most straightforward way of doing that is to just think about the two effects separately. So we have an effect of age. That effect of age determines the slope of the lines. Then we have an effect of constituency type. That effect determines the average and thereby the intercept. So if we assume that the two effects are separate from each other in that way, the only additional piece of information that we need for our equation is this offset, is the difference between the intercepts. We can easily get that extra piece of information with the LM function by adding the constituency type to the formula. Then in the model output, we again get an estimate of the impact of age. But this is now the impact of age, keeping constituency type constant. So you might notice that it's a little bit lower than it was before. Likewise, we get an effect of constituency type holding age constant, and we can see that borough constituencies indeed have a slightly lower conservative vote share than county constituencies. Now, when both variables are in the model, it's much less so than if we don't consider age. We can look at R squared, and that actually seems to indicate that we haven't explained any additional part of the data. So we're still explaining 30% of the variance, are leaving 70% unexplained. We're now just using two variables to do so. If we now plot this visually, we have two parallel lines. And we can see that age seems to be having a much greater effect than constituency type. What we have just done here, by adding the categorical variable, is we have used dummy coding. We clearly can't use a word like county or borough in a mathematical formula. So instead we need to use binary indicators that are just yes-no indicators. And conventionally we say 1 is yes, 0 is no. If we have more than 2 possibilities, we need to use more than one indicator. So, for example, we might have a variable of a student's department with 3 answer options. Now we would need to use 2 indicators to indicate, well, is the student in psychology, yes or no? Is the student in curriculum, yes or no? We don't need a 3rd variable, since we know that there are only 3 options. So a student who is not in psychology, not in curriculum, must be in the 3rd option. But then that 3rd level becomes the reference level against which the others are compared in a regression model. So now that we only had 1 level in the voting model, it made sense to immediately notice that borough, that was printed, must have been compared against county, that was not printed. But if we have more than 2 possibilities, it's important to really keep in mind which one the reference level is that we're comparing against. Also gives us an idea that using categorical variables in regression is best when there aren't too many categories. Because for each additional category, we're adding 1 additional variable into the model and 1 additional line into the plot. So it's not very helpful when there are too many categories. Okay, so this was the first extension. Instead of 1 line, we now have a couple of parallel lines. What happens if we want another continuous variable? In the election case, we might be interested in whether deprivation, so local poverty, also contributes to explaining the conservative vote share. If we do a simple linear regression analysis, it seems to do. We can see that for each rank in a constituency deprivation, the conservative vote share declines by 0.05%. But how does that now fit together with age? We again want to put them into 1 model. So how can we combine them? Mathematically, we're interested in exactly the same information about each of the variables. We're interested in how a change in one of them affects the outcome variable. So we can literally just add a second slope to the regression equation. In R, we might be tempted to just add it to the LM function call, and we can do that. But what does this now mean geometrically? What is actually happening inside these models? Before, we had 2 dimensions and fit a line. Now, we're going to 3 dimensions and we're fitting a plane. What does that actually mean? So, in terms of the scatterplot, we now have a 3D scatterplot where each point is characterized by 3 coordinates. Each constituency has a median age, has a deprivation level, and has a conservative vote share. So we have this cloud of points, and we can now fit a plane through them that is as close as possible to each of the points. That's then the regression plane. In exactly the same way that the line did not cross all the points, the plane does not go through all of the points, but rather each point still has a distance to the plane. That's our prediction error for that particular point, the so-called residual. If we now run the LM function with this particular model, we get very similar output to what we had before, with basically just 1 extra line, because that's all we need to turn a regression line into a regression plane. So again, we have our 2 coefficients that indicate the effect of that particular variable on the outcome variable, holding the other predictors constant. So age still has an effect on the vote share, but actually a somewhat smaller effect, given that this time around we're holding deprivation constant. Similarly, deprivation has an effect. They are both significant because they're very small p-values, so we can be quite confident that they're reflecting real differences rather than just noise in the data. And we can look at the R-squared, we can see that actually this model explains much more of the data than the last model did. However, one interesting question that we can't answer from this output is which of the two predictors might be more important. We have two numbers, but they have different units, so we can't compare those two numbers. The way to go about that is something that you might be familiar with, because it's very similar to an idea we already discussed. It's all about standardizing the data. So whenever we have different units, a way to go about it is through standardization. Standardization, specifically in statistics, tends to mean making z-scores. So expressing the data in terms of standard deviations rather than in terms of the original units. We encountered that so far through correlation coefficients, where we standardize two variables, run a simple linear regression, and get a standardized correlation coefficient. Here the standardized beta coefficients are very similar. They are just what we get when we have more than one explanatory variable. We can run it in this rather complicated way by manually standardizing each of the variables. Then the output contains standardized coefficients, and we can now see that indeed age seems to have a stronger influence than local deprivation. Because now we have two numbers that are in the same units. This is helpful because it allows us to make these comparative evaluations. If we want to use this, we usually wouldn't calculate it in this rather cumbersome way, but there are of course specific functions for it, for example in the quant-psych package. Okay, so let me recap the different model types with a different set of examples. Let's think about wanting to predict grades on the upcoming statistics exam. So, very simple linear regression question might be, can we predict the grade based on how much a student has studied? For that we would need to fit a regression line and check the coefficient of that line. We might want to make the estimates a bit better by also adding whether the student is doing qualitative or quantitative research and thereby just has exposure to statistics as a categorical variable. With that, we would then get parallel regression lines, but possibly somewhat better estimates. We might decide to consider more than one continuous predictor. So for example, we could consider independent study time and the number of sessions attended. We wouldn't want to do it in two separate models because they're probably correlated to each other. So we want to run one model with both of them, find the regression plane, and then see whether that plane is useful in predicting results. We might do that and add a categorical predictor back in, and then get parallel regression planes. We can keep on going, adding more predictors, but the geometrical intuition probably stops here, because most of us are really not good in visualizing more than 3 dimensions. But mathematically and programmatically, the process can just go on if we have more predictor variables, explanatory variables, that we want to test out. There's one special case we have already looked at, which is the case when we just have one categorical predictor. For example, in the case when we have multiple groups. So we might want to ask, we have these county and borough constituencies, but does that affect turnout? Is the turnout higher in one constituency type rather than the other? If we just care about 2019, that's a question purely about descriptive statistics. We can look at the averages and see, well, turnout in 2019 was higher in county constituencies. However, we might want to see those results as a sample drawn from a larger population of election results across multiple election cycles. And then say, well, how likely could it be that this difference is just due to chance? For that, we would need to then run an inferential statistical test. And before Christmas, we discussed t-tests as a way to do that. However, that's just a special case of a linear model. As always, it's a good idea to plot the data. And here it looks like there really is a difference between these two distributions. So we could run a t-test, but in fact we can also run a linear model. The linear model then seems to tell us that there is a significant effect and it estimates slope. But what does that slope mean in the case of a categorical variable? Well, it helps to think about dummy coding here. The way this is coded is that borough is represented by 1 and the reference level, county, is represented by 0. So the step from county to borough is exactly 1. And the slope tells us the impact of a step of 1. So this is now equivalent to the difference in the two means. It's one of those rather many cases where a specific statistical test, such as the t-test, is just a special case of linear regression. Sometimes it's worth using the special tests for ease of interpretation because they're commonly used. Sometimes we can also just stick to the linear models. But what to remember for now, before we explore this all further in class. So the first point is that linear models are this very versatile statistical tool that allows us to describe the relationship between a variable that we want to explain, as long as that variable is continuous, and any other variables, regardless of whether they are continuous or categorical. There are a couple of important assumptions that limit the situations when we can actually use linear models. The most important one to really bear in mind is that we are assuming linear relationships. So it's worth plotting the data and worth thinking about whether these linear assumptions make sense. If I wanted to study the effect of caffeine intake on exam performance, for example, I could not expect that that's a linear relationship, so I would need to use a different model. We'll explore other assumptions next week, but keep the requirement for linear relationships in mind. The other thing to take away is this intuition of what the steps are. So the first step in a linear model is to fit our predictions into the space of the data. When we only have 2 variables, it's a line. When we have 3 variables, it's a plane. When we have more variables, it's a hyperplane that we can't really visualize anymore, but the first step is this fitting process. The second step is to then look at basically descriptive statistics, at the slopes. And then the third step is to check for statistical properties of the model. So can we actually expect or reasonably believe that the coefficients, the slopes, are different from 0? And how much of the data does the model actually explain? That's R squared, that's the fit. And then the last point is to remember the difference between standardized and unstandardized regression coefficients. Unstandardized coefficients tell us about the change in our outcome variable per change in the explanatory variables using their respective units. So that's often easy to interpret, but it's not comparable across variables. If we want to figure out whether age or poverty is the stronger predictor, we need to standardize the variable. We need to get the so-called beta coefficients, the standardized regression coefficients. So with that, thank you for watching. Please try to have a look at the book chapter that is linked below and in the email, and then I'll see you in class.